Hello and welcome to this introductory video on superposition and interference. In this video we are going to be taking a look at answering a very key question, which is what happens when two, or more in fact, waves meet at some location. And the answer to that question comes from the first word there, which is superposition. You've actually been doing superposition a lot before. When you, for instance, were asked questions about what's going on with the electric field when there's multiple charges, you realized that you just took each individual field and you added them. And then you said that the total field was that sum. And of course you added them as vectors and got some overall weird direction maybe, but that vector sum was the net field. And forming that net field was actually taking a superposition of each individual field. So the word superposition really just means add things up. Okay, so that's what we're going to do. Let's think about, in this next slide, two waves, the green and the orange, moving along, and then we've frozen time. At some points in time, this is the sort of thing that might happen. They might perfectly match up, so that's why you can't see them both right now. They perfectly match up, they're one on top of the other. In that case, when I add them, I get this blue line, and that blue line, now, as you see, has the same wavelength but double the amplitude. This sort of phenomenon is what we call perfectly constructive interference. Now, we use the word interference. It's really just a fancy way of saying the combined effect of the two waves. Or really, just another way of saying that we've added things together. So, the perfectly constructive means that these things are everywhere in phase, and therefore they are always giving rise to a doubling or a sum of their individual amplitudes, which in this case happens to be the same, so we get a doubling of the final amplitude. So you can see how that's twice as high. Okay. If they're not in phase, well, here we go. This is some time when they're not in phase. You see that blue wave changing. If we freeze time again, this is another special case. These are now completely doing the opposite thing. This one is at a peak when this one's at a trough. So we call the negative peak a trough. And they're just doing that exactly all the time. Whatever this is positive, that other wave is doing as a negative oscillation at that time. So when I add these two together, you can see the blue line has vanished. It's just along the axis there. So it's completely been suppressed. They're canceling each other out. This is, as I said, another special case. This is called perfectly destructive interference because we've basically destroyed, at least in terms of the actual amplitudes of oscillations here, it seems like we have destroyed the wave. All right, these waves, interestingly enough, as you'll see in a moment, are still moving along. So we haven't actually destroyed the wave, but what we've done is at least destroyed the oscillations. And it happens because these things are completely out of phase. So this is what we mean by them doing the opposite thing. If I'm at a peak and the other one is at a trough, then these things are exactly 180 degrees different in their phases. And that is what we call a condition for being out of phase. And when that happens, we get perfect destructive interference. In the case of two equal amplitudes, we get cancellation. If it's not two equal amplitudes, well, then this gives the sort of minimum amplitude of oscillation possible. Now, as I said, these things are going to keep moving. In fact, I don't have to show you that they in fact do keep moving. This is exactly the video, or the frame of the video at which we started. So this is how our, if you just dial back the video, you'll see this is how the wave started. They will then move, give rise to a perfect constructive interference again, and then they'll come back to this state, and they'll just keep cycling back and forth as these waves continue to move against each other. And what we look at, if we just take away the individual waves and we look at the sum, what the sum is doing is it's just doing this. It's just oscillating up and down. You'll see that there are some points which don't move. We call those nodes. And then there are the peaks. So the maximum displacement part, this is always going all the way up to 2 if we're talking about being in terms of the original amplitude, and going down to -2 of the original amplitude because we're just doubling things. So this thing is doing the maximum motion. We call that an antinode. And these points here, which are not moving, are our nodes. Okay, and this whole thing is called a standing wave. It's called a standing wave because, as you see, this thing, which is the superposition of two moving waves, is not moving in itself. So we call it a standing wave. It is only possible to create a beautiful standing wave like this when you've got the two identical waves.